Hello, my name is Subili. I am a PhD candidate student in the Visual Computing Lab at 성균관대학교 University, supervised by Professor Jeffrey He. Today, I would like to present task-oriented channel attention for fine-grained viewshot classification. This paper was published in TPAMI 2025. Before diving into the main explanation, let me first briefly introduce our research lab. Our Visual Computing Lab is led by Professor Jeffrey He, and we actively conduct research on a wide range of computer vision and machine learning tasks. As shown on the screen, we deal with almost tasks from the basic downstream tasks like recognition and segmentation to generative models. Furthermore, as evident from our 2025 publication list, our lab is highly motivated and continuously strives to become a top-tier research group. For more detailed information about our lab, please refer to the URL link provided or search SKKU VCLab in Google. Additionally, while many of you may be familiar with conferences such as CPL and NIPS, information about TPAMI might be less well known. Therefore, before diving into the details of our paper, I will provide a brief introduction to TPAMI. IEEE Transaction on Pattern Analysis and Machine Intelligence is one of top-tier journals in computer vision and AI. Typically, it publishes extension versions of papers that were previously accepted at major conferences like CPL and NIPS. In fact, the paper I am presenting today is an extension version of our CPL 2022 paper, which was accepted as an oral presentation. Unlike conferences, TPAMI has a much strict review process, ensuring that the published papers are of the highest quality. For instance, this paper underwent a review process of nearly a year before being accepted. Now, let's dive into the details of our paper. Deep learning has surpassed human performance in various domains. However, this success heavily depends on the availability of large-scale datasets. To address this limitation, the concept of few-shot learning has been introduced. Few-shot learning aims to develop models with high adaptability to new classes using a small number of labeled data. Specifically, the models learn knowledge about new classes from a small number of labeled data support set and then estimate the information of the unlabeled data query set. Few-shot classification refers to the classification task with this few-shot learning framework. Typically, in few-shot classification, the category of a query sample is determined based on its distance to support sample in the feature space. This approach is known as metric-based few-shot classification, which is widely adopted in most few-shot classification models. Previous metric-based few-shot classification approaches are effective in coarse-grained scenarios where categories have distinct visual difference. However, they can be inefficient in fine-grained scenarios where categories share highly similar appearance. This inefficiency arises for the following three reasons. First, lack of discriminate feature. In fine-grained classification, visually similar classes have very few discriminative features and share many common characteristics. Therefore, there are almost no difference between those categories in the feature space. As a result, it's becoming challenging to differentiate them based on distance. Second, mismatch of discriminative feature between support and query. Even if there are discriminative features between categories, those features might exist only in support sample and not be present in the query samples. In such case, we cannot predict the category of the query based on those discriminative features. Therefore, we should verify whether the discriminate feature of each class exists in the query sample. Last, ineffective feature extraction for novel classes. Since the feature extractor is trained with base classes, it is not optimized for those novel ones. Therefore, the feature extractor may fail to extract the discriminative feature of novel classes, or it may capture background feature. As a result, in order to capture discriminative feature of novel classes, the feature extractor should compute feature around the object of the novel classes. To address this limitation, our approach includes three key modules: support attention module, query attention module, and instance attention module. First, the support attention module enhances class-specific discriminative feature by assigning high weight to the most relevant channel. At the same time, it reduces the impact of commonly shared features across all classes by giving them lower weight. On the other hand, the query attention module focuses on the features that are actually present in the query image. It prevents features that do not appear in the query from affecting distance computation. In other words, it filters non-query object relevant features. Last, the instance attention module improves feature extraction by guiding the model to focus on object relevant information. It enhances importance channel while suppressing background noise. As a result, it leads to better feature representation for not only base classes but also novel classes. In fine-grained feature classification, one of the biggest challenges is distinguishing between visually similar categories. Many objects from different classes share common features such as bird having similar beak, wing, or body shape. Since only a few labeled samples are available for each class, it is crucial to focus on the most discriminate part of an object rather than treating all features equally. To achieve this, we first define salient object regions within the feature map. Each channel in a feature map typically captures specific object characteristics such as texture, color, or shape. By applying global average plane along the channel axis, we aggregate information from all channels to generate an approximate object segmentation mask at the feature level. This allows us to estimate which area of the feature map corresponding to the object while reducing the influence of background regions. As shown in the figure, individual feature map channel may highlight different parts of the object, such as the head, wing, tail. When we take the average across all channels, we obtain a salient object region map that represents the overall object area within the feature map. To evaluate the importance of each channel in the feature map, we define two key metrics, intrascore and interscore, based on salient object regions. First, the intrascore measures how well each channel corresponds to its own salient object region. Each channel in the feature map captures different aspects of the object, but not all channels are equally relevant. By computing the distance between each channel and its corresponding salient regions, we can determine how object relevant the channel is. If a channel strongly aligned with the object's salient regions, it will receive a lower distance value indicating higher relevance. On the other hand, the interscore assesses how distinct a channel is from other objects. Even if a channel is highly relevant to an object, it may not be useful if similar features appear in other categories. To measure this, we compare each channel with the salient object region of other classes and compute the minimum distance. A high interscore indicates that the channel captures unique features that are not shared across different objects, making it more discriminative for classification. To achieve effective feature representation, we need to identify discriminate channels, those that capture essential object information while being distinct from other objects. A truly discriminate channel should exhibit low interscore, meaning it's strongly aligned with the object on salient region and focus on relevant features. And it also exhibits high interscore, ensuring that it does not capture commonly shared features across different objects, but rather highlight unique characteristics. As illustrated in the figure, some regions such as the bird beak or wing pattern may be similar across different classes. Channels that focus on this shared feature will have both high intra and low interscores, making them less useful for classification. In contrast, channels that emphasizing truly discriminate features such as unique pedal marking or shape variation will exhibit low intra and high interscores, making them ideal for distinguishing between classes. By prioritizing channels with high discriminative power, we ensure that the model focuses on the most informative and class-specific details. Ultimately, it leads to more accurate classification. As mentioned earlier, the fine-grained feature classification should focus on discriminative features rather than common features. To achieve this, we designed the support attention module. The support attention module generates a weight vector that emphasizes class-specific discriminant features. To achieve this, it processes the intrascore and interscore which we previously defined through a fully connected block. Through this process, the resulting weighting vector assigns higher weight to channels with low intrascore and high interscore, this meaning they capture more discriminative information. By leveraging these support weight vectors, the model can focus on more effectively on distinctive features of each class. However, as previously mentioned, some of the highlighted features may not be present in the query object. To identify the feature that actually exists in the query object, we designed an additional submodule, the query attention module. Unlike the support set where class labels are known, we cannot access the label information of the query set. Therefore, the query attention module is designed to utilize only the intrascore for generating the query weight vector. By leveraging the query attention module, we obtain a query weight vector that assigns higher weight to channel relevant to query object. This allows the model to focus specifically on query object relevant feature, bring improvement classification across. By combining the support weight vector and query weight vector generated by the two previously mentioned submodules, TDM produced a task weight vector that emphasizes the discriminative features present in the query for each class. By multiplying this task weight vector with the original feature map, we can obtain a task-adaptive feature map where the query objects discriminative features are further enhanced. As a result, using the task-adaptive feature map instead of the original feature map allows us for more efficient and accurate classification of the query object. However, both the support attention module and query attention module assume that the feature extractor performs well even on novel classes. To ensure that the feature extractor effectively captures object-relevant features for novel classes, we introduced the instance attention modules. The instance attention module operates similarly to the query attention module, but there is one key difference. Each weight is applied only its own feature map. Even for novel classes, most channels still focus on object-related features. As a result, the weight generated by the instance attention module assign higher values to object-relevant regions. Ultimately, the instance attention module helps guide the feature extractor to focus more on the object itself. Then, it leads to more effective feature representation. Before analyzing the performance, let me briefly explain the evaluation protocols for feature classification. Feature classification is typically structured as an n-way K-shot setup. This means that the model must correctly predict the query class among n candidate classes, where each class has k-labeled support sample. To evaluate the model across various n-way K-shot composition, we use the episodic evaluation protocol, which consists of three main steps. First, randomly sample n classes from the test dataset. Then, extract k support samples and u query sample from each sample classes. Last, predict the query class based on the support set and compute the accuracy. This process is typically repeated 10,000 times, and the final model performance is reported as the average accuracy over all episodes. Based on the previous evaluation criteria, our method demonstrates the following performance result in fine-grained feature classification. Since our approach is module, we applied it to 4 different baseline models: ProtoNet, DSN, CTX, FRN. Across all baseline and scenario, our method consistently leads to performance improvement, and this demonstrates that our method is well designed and highly applicable to existing methods. Furthermore, since our method applies weight to the feature map, the performance gains are not merely due to the increase in the number of parameters. Instead, the improvement comes from effectively distinguishing task-relevant channels and assigning higher weight to most useful features for solving the task. Moreover, like SAM and QAM, which are specifically designed for fine-grained feature classification, IM also demonstrates effectiveness in coarse-grained scenarios. What even more remarkable is that IM, which operates through channel attention, is compatible with V8 backbone that utilize spatial attention. This suggests that IM has the potential to be widely applicable to various tasks in the future. In general dataset, the feature map which contains various object information is widely known to be beneficial. However, in fine-grained dataset, since categories share a common overall appearance, it is more effective to focus on discriminated regions. In fine-grained feature classification, unlike standard fine-grained classification, the discriminated regions may vary depending on the composition of the episode. Thus, dynamically identifying these distinctive features within each picture is crucial. As shown in the figure, the baseline model treats all characteristics equally regardless of the episode's composition. In contrast, TDM adapts by focusing on the most discriminating part and suppressing the common feature. As a result, this makes TDM is a highly specialized module for the fine-grained feature classification. We have extensively validated the effectiveness of our proposed module in various scenarios. However, in previous experiments, the number of classes per episode was fixed to 5 following existing protocol. In real-world applications, the number of classes can vary depending on the situation. To assess the robustness of TDM of IM under such conditions, we evaluate their performance across different NA settings. As shown in the above figure, TDM and IM consistently improve performance across various class compositions except for one case in the 5-shot aircraft benchmark. Moreover, the relative performance gain increased with the number of classes. This provides that our modules are more effective in challenging scenarios with more categories. Similarly, we also examine the impact of varying the number of labeled images per class. As shown in the below figure, our findings indicate that the benefits of our module are most pronounced in the low-shot scenario. This reinforces their effectiveness for future learning while remaining beneficial even in many-shot scenarios. The support weight vector is computed using linear interpolation of intra and interweight vector from intra and interscore respectively. However, there are some alternative integration methods like SEMDIP and SEMDIVE. SEMDIP uses the difference intra and interscore to compute support weight vector. On the other hand, SEMDIVE utilizes the ratio of intra and interscores. Both approaches lead to significant performance decline, likely due to scale difference between intra and interscores. Thus, we conclude that weighted interpolation with pre-connected block is most effective since it normalizes unbalanced score across dataset, ensuring stability. To further verify the benefit of our method over existing attention modules in the fine-grained feature classification task, we compare our method with other attention modules. As reported in the table, our method outperformed the existing attention method by a large margin. Note that the main difference between our method and the existing modules is that we explicitly measure and leverage the channel-wise importance based on the representative scores in our attention module, while existing methods rely on the learnable parameter less suitable for the few-shot and fine-grained scenarios. Consequently, these results confirm that our modules has clear benefit over existing attention module in the fine-grained feature classification task. To sum up, our contribution is as follows. First, we propose a novel feature alignment method for fine-grained feature classification. Second, we further develop IM that highlight the object-relevant channel with the intermediate layer of the feature extractor. Third, our proposed method is highly applicable to prior metric method. Last, we record the state-of-the-art performance in fine-grained feature classification task. Additionally, while our paper includes various other experiments and analyses beyond what we covered today, we could not discuss them all. If you have any questions about the paper, please feel free to reach out to me through our left website link. Thank you for listening to the presentation for a long time.